Section 8.5. In this section, we'll use the household reflectors for the construction of Q and R for QR factorization. Let's begin with a corollary which we considered earlier. A is a square metric, then there exists an orthogonal metric Q and an upper triangular metric R such that A is QR. We'll try to prove this corollary. The proof will suggest a reasonable algorithm for QR factorization. The proof is by induction on N. Mathematical induction is formulated as follows. We'll assume the claim is true on a step, then under the assumption, we'll try to prove the next step claim is true. So once the first step is true, then second step will be true, and third step will be true, and so on. So here we start with when n is 1, then A has one component, A11. We can define Q is just 1, then R is same as A, then A is QR. So the claim is true when n is 1. This is the first step. Now for n larger than or equal to 2, we assume that QR factorization exists for n-1 by n-1 matrices. Now we'll try to prove that QR factorization exists for n-dimensional matrices. Okay. We start with Q1, a reflector, for the first column of A1, Q1 A1, okay, that is A1, first column, is now minus tau 1 and 0 all the way down. Of course, tau 1 must be plus minus length of A1. We considered such a reflector in the last section. So we have always such a reflector. Then, now Q1 transpose is multiplied to A. It's symmetric, so it's a Q1A. Now, first column will be transformed into that over there, and something. And again, we have here something. But that one will be n-1 by n-1. The assumption is saying that we have QR factorization for this part. Okay. So A2 hat is Q2 hat, R2 hat. This is orthogonal metric, and R2 hat is upper triangular metric, right? Now Q1 has n dimensions, but Q2 hat has n-1 dimensions. So to match Q1 and Q2, we need dimension expansion from Q2 hat. So we add here 1, zeros, and zeros. Then Q2 will have n dimensions, so that now along with that, we try to multiply Q1 transpose, Q2 transpose 2A. That's the result of Q1 transpose multiplication, and Q2 head is multiplied here, Q2 transpose. Then now, okay, and because of that, and this one will be transformed to R2 head. This whole thing is upper triangular. So along with this one, we reach at upper triangular, so that it's inverse, so that eventually now Q1, Q2 will be the orthogonal metric, so that A is QR. That's R. So once we define Q as Q1 and Q2, then clearly A must be QR. So we got QR factorization. That is an example of mathematical induction. We have a remark. Q is identity minus gamma U transpose from a vector to y is minus tau in zeros, so that tau must be plus minus, okay, length of x, and also gamma must be 2 over u norm squared, right? And of course, u is the same as x minus y. Now, u is the same as x minus y, right? We know that. Now, once you try to get x minus y, then for x, now first component will be changed into x1 plus tau. And originally, for x minus y, we have here x1 plus tau. And we scale it, then now it'll be 1, and we have these quantities. So scaled u has these values. It's quite beneficial. The computation of u length is easier, and also this is always 1, so that we can use this position to save something else. We don't have to save this value. It's always 1 in the beginning, so that we can use the position. Now, for this scaled u, let's try to get length of the vector. Okay, u norm squared. That is, now first component originally is x1 plus tau squared, second one squared, and so on. And then that quantity squared. But this square is the same as x1 squared plus 2x1 tau plus tau squared. Right? Now, using that one and remainder over there, we have x norm squared. So we reach at that quantity for the numerator. Now, tau is plus minus x norm, so the tau squared must be same as x norm squared. Right? So this one and that one are the same. So we have 2 tau squared and 2 tau x1. So we can factor out 2 tau, and we can cancel tau plus x1, bottom and top. So we reach at this quantity. So overall, what we need is gamma 2 over u norm squared. By using this quantity, we reach at that one. So gamma can be easily computed along with this formula, x1 plus tau over tau. Okay? The proof of corollary 8.46 suggests an algorithm for the construction of Q and R, we start with the first column. So Q1 is formulated in this way. Identity minus gamma 1, U1, U1 transpose. Of course, U1 is made from the first column, and then now the minus tau and 0, 0, 0 transformation, and x minus y, in fact a1 minus y is scaled by this factor, and then u1 is made. Along with this u1, gamma 1 can be found correspondingly by using this formula. Okay, and then also, and after transformation here, okay, once Q1 transpose is multiplied, then and the result will be now in the matrix there is a minus tau and something, there is 0, 0, 0, and over there. And for this part, only we focus on this part, and we can formulate this reflector exactly the same way as for Q1. But now we have to match the dimension, so we put here 1, 0, 0, 0, 0. In general, later on, we can formulate the reflector and match dimension. In general, at the case step, we have that. Now, if we consider the multiple of these reflectors and Q, then Q transpose A must be on a triangular matrix. So that we done. That is the orthogonal matrix. But in this computation, we don't need the form Q1 to Qn minus 1 explicitly. For example, for Q1, and that is identity minus gamma 1, U1, U transpose, rather than the formulating Q1 explicitly, we try to save only and minus tau 1, gamma 1, U1. But once you try to form Q1 explicitly, then the cost is order n squared. Now, once you save these quantities and vector, and for each column of AK, now Q1 transpose AK is now using the formula, we reach at this one. Now, this one, that in the product is a scalar, so we reach at that one. This dot product will require 2n flops, and about 2n, and then along with this constant, this linear operation requires again about 2n flops. So the total 4n flops are required for each column. So when we try to transform whole matrix, then there are here there is 2 to n, so that there are n minus 1 columns, so that the cost of this transformation is about 4n squared. So that is the computational complexity for that transformation. Okay. Here we have the QR factorization by household reflectors. A is a square matrix, and K is moving from 1 to n minus 1 for each pivot column, we can formulate the reflector. Of course, we considered this one earlier, and that is the pivot column will be transformed into a non-zero entry, and everything else below will be 0. Of course, this tau k is plus minus length of this pivot column. Okay. Now, gamma 1, gamma k also will decide it correspondingly. We know that. Now, we save the UK on the pivot column. And then the first component, and UK is scaled the vector, so that the first one will be 1. So that for the position minus tau k will be saved. Earlier we said that we need only store minus tau 1, gamma 1, u1. So these two can be saved over the matrix A. Now gamma 1 must be saved separately in an array. Okay. Now this portion is transformation for the remainder part of the matrix, and we save finally the gamma k to a separate array. And the last moment, the last bottom right corner value can be saved into this array, the last the spot. And once it is a non-singular, then usually it's non-zero. However, the matrix is singular, then this value is 0. Here we have note the QR factorization by reflectors. The output is saved over A. So upper portion is just there, and eventually that must be R after the computation. The upper portion must be R. Recall that the flop count for case 1 is about 4n squared. For case 2 is about 4n minus 1 squared. For case 2, now the computational cost must be about 4 times n minus 2 squared and so on, so that the total cost for QR factorization by the reflectors will become this quantity, which is about 4 over 3 n cubed. That is about twice of the cost of LU factorization. So for solving linear system, the QR factorization is not much used because the cost is twice, and LU factorization is more popularly used. But QR factorization is useful for many applications, and so that it will be very frequently used. Okay, each of these QK household reflector is symmetric and an involution matrix. Of course, it's orthogonal, but this product is not symmetric, nor an involution matrix. However, it is still orthogonal. So that's fine. We need an orthogonal matrix, symmetry, or some involution is not really required. So that's good enough. The matrix A is a singular if at least one entry of G is 0, particularly the last one, last component is 0, then A must be singular. Let's see an example. Use reflectors to get QR decomposition of metric A. Okay, for this one, we'll try to get Q1. Now, for that one, we select from the metric the first column, and tau 1 is made the positive, the first column length. And now, once, so we have to choose either positive or negative, but the manner is here. The first component is less than 0, then we try to get tau 1 is negation, so that eventually we try to avoid the A11, okay, A11 plus tau 1 is not near around the 0. So in modulus, we want to get it as large as possible. So that is the way of deciding tau 1, and tau 1 is in fact plus or minus norm of A1, the first column, but we have to choose the sign through this checking. Okay. Now U1 is A1, and then now we can find here scale, and then the first one is 1, and then the remaining part is just divided by scale. And now here scale divided by tau from earlier formula, that is now G, the first component of G. Okay, that's it. Quite simple. And for that one, here Q1 is identity minus G1, U1, U transpose. That is it. And then now Q1 transpose A is made, and floating point, the values are given in this way. Now, so that after transform, this below is 0, and we have only a non-zero component, and this one. So that Q2 will be made along with that one. We are focusing on this one, and then Q2 will be constructed. Okay. Here we have the portion for Q2. The manner is exactly the same, but only the difference is now we have to embed to a larger metric so that dimension should match. Everything is the same, and then eventually we have to get the embedding. Okay, so after embedding, we have that. Okay, that is Q2. And here, let's check if it is okay. Now, Q is, now Q1, Q2, and now here we can see this matrix. So this is Q. And once 2A, Q1 transpose, Q2 transpose multiplied, then we have upper triangular. And once QR are multiplied, then we can get the original metric A. Here the values are numeric values because of that command is evaluation for floating point numbers. But here Q itself has two values, and a very complicated way the values are given like over there. Q1 has these exact values, but now once you try to evaluate n for floating point numbers, then now it can be simplified. Of course, over the Q&A is also quite complicated exact value, but here floating point numbers are given in this way. Okay, so that QR multiplication will have exact value. There's no round error added. Okay. Now let's try to check using the built-in command. In Maple, the command is QR decomposition. Then we have that. Now we can print out the numeric values, and we can compare this and over there. Okay. Now only the difference is a sign every year, and this computation is now is done without considering diagonal entries. But earlier we considered the theorem saying that once R has diagonal entries positive, then the QR factorization is unique. So we considered such a theory. So in default, the built-in function has such output. Try to make it everything positive when it's non-zero. Okay. So eventually, we can see the output is the same. And once it is manipulated, look at over there, minus 6.7823. There's same amount, same magnitude. Okay. Okay, that's the end of the section. Thank you.